Alright, this is presumably the last video of the second week. So now I'm cover chapter 16 in Musgrave Winston Green. So we begin our systematic study of general equilibrium in comparative markets. So in this video, my plan is to cover up to first welfare theorem. So let me postpone the second welfare theorem to next week. Alright, so we are going to study interaction between consumer and firms in market mechanism. So first, I'm going to introduce general framework for economic analysis, for general equilibrium analysis. So there are, in that framework, there are many consumers and many firms, okay? And they interact each other in a market mechanism. What I mean by market mechanism, this mechanism is based on two assumptions. The first assumption is a price is quoted for every commodity. We call this assumption market completeness. So market is complete. Market is complete. In the sense that every commodity has a unique price. And this assumption does not hold, especially in case of public goods. So in the presence of public goods or in the presence of externalities. So think about public goods. That's a leading example of positive externality. Air, national parks, whatever. And for those goods, property rights are not well defined. So we can price those goods. So in such a case, market is going to be incomplete, right? So that's a first important assumption in market mechanism. And the second assumption is more important. All agents take these prices as given. Okay, so all consumers and firms are price takers. So prices are determined only through competition in market. To each economic agent, price is beyond control. Price-taking behavior. So market mechanism stems from these two assumptions: market completeness and price-taking behavior. Okay. So based on these assumptions, we are going to study interaction between consumer and firms. So that's a limited interaction. So that's why we study game theory. There's a more general interaction without these assumptions. All right, so this is called the comparative market. So the price is determined by competition. And the main objective in this chapter is to establish the link between market equilibrium and efficiency. So we are going to study two welfare theorems. We've seen these two welfare theorems in previous examples. So first welfare theorem means Wallachian equilibrium is Pareto optimal, and the second welfare theorem implies every efficient allocation can be achieved by the use of a market mechanism with wealth redistribution, but that's going to be postponed to next week. All right, so in this video, I'm going to introduce general framework and introduce a first fundamental theorem, and I'm going to prove that theorem in that general framework. All right, so the model, now the economy, consists of L commodities and the I consumers and J firms. Okay, so, and these economic agents are interact with each other, and the consumers have a L commodities, and firm also produce some units using some inputs. So these commodities involve all outputs and all inputs. So there are total L commodities. And let me first explain consumer. Okay, so for each consumer I, so consumer is indexed by I. So there are total capital I consumers. And we first need to define consumption set, what each consumer can choose. So each consumer can choose one bundle consisting of L commodities. Okay, and some might be input, like a leisure choice in the Robinson Crusoe economy. So some commodity can be used for production, and some commodity can be used for just a consumption. So here, this is a consumption set. So very general definition of a consumption set. All right. So the consumption set is the set of bundles consumer can choose. Okay. And so it has nothing to do with the budget constraint. We did not define budget yet. Right. And the consumer firm's preference relation on this set. Okay. So the preference relation denoted by this curly inequality. So that stands for so that firm's binary relation between two bundles. Okay, and we assume this relation is complete, meaning that consumer can tell which bundle is preferable to another, and transitive if a x is preferred to y and y is preferred to z, then x is preferred to z. Okay. And if a relation satisfies these two axioms, we say preference relation is rational. Okay? And we need one more technical assumption, continuity. So I think you guys have studied that lexicographic preferences do not satisfy this continuity assumption, this continuity axiom. Okay? But if relations satisfy these three axioms, then we have a continuous utility function that represents consumer's preference relation. So meaning that if consumer prefers x to y, bundle x to bundle y, then this u function gives us a higher value, and the other way around. Okay? If u of x is higher than u of y, then consumer prefers bundle x to bundle y. So in that sense, u of x represents consumer i's preference. And each consumer may have some initial endowment, just like a labor force. We have so working hours per day, say 16 hours. So that is an initial endowment. So some consumer may have some initial endowment of commodity, like a apartment, property, or whatever, capital, whatever. So that endowment is denoted by omega I. Okay, so omega I is a vector. So L commodity vectors. So it stands for consumer I's initial endowment. Okay. So for each commodity K, we define omega K upper bar as a total endowment of that commodity. So that is a summation of omega Ki across all consumers. Okay. And omega bar, that is a L vectors, so L tuple vector. So it contains all initial endowments in this economy. All right. Finally, firms are owned by consumers, right? Firm is an institution. So we have to define consumer I's share in that firm. So theta zi, that is a number between 0 and 1. So it stands for firm's share in firm J. So if theta ji is equal to 1, that means firm J is fully owned by consumer I. So it's a full ownership. So if that equals 1, meaning that full ownership of firm J by consumer I. Okay, so theta I. So let me use a superscript for consumer, and I'm gonna use a subscript for firm or commodity. All right. So theta I is a Z tuple vector. So it stands for from consumer I's ownership over J firms. Okay. And of course, for each firm, if we add a theta over all consumers, then the ownership should be equal to 1. So each firm is owned by I consumers. Okay. Now firm side, and there are J firms, okay? And each firm's technology is described by this production set, right? I think I illustrated this production set when I illustrated Robinson Crusoe economy. So that is a little bit more general than production function. So each element of this set stands for a production plan. So it consists of a L components. So if a y sub kj is a negative, then meaning that firm J uses commodity K as an input. If that is a positive, then firm J produces commodity K as an output. All right. So the sign of each component has a economic meaning. Okay. And then production technology is given by this frontier. So in case of one input and one output, we study production set is given by this. Okay? So that appears in the second and third quadrant, meaning that this firm uses a component on the x-axis as an input and produces component on the vertical axis. So if one production plan is an element of this set, that implies that this production plan is feasible. Okay? If that is not an element, then it is infeasible. Okay? So the firm's production technology is given by this general production set. And we make some assumptions on this production set, that is origin is an element of this production set, meaning that the firm can shut down anytime without any cost. Okay? If there is some sunk cost in that production, then the origin is not an element anymore. So now the production set starts from this point. So that stands for some sunk cost. So the firm has to use this input even when the production is shut down. So that stands for a sunk cost. But we do not consider such a sunk cost. So it is a long-term plan, okay, long-term plan. And we assume production set is closed and convex. Okay. So in case of so if we have a production function for each firm, convex set means production function is concave. So we have a diminishing margin of productivity. Okay. And how does the firm behave? That is pretty easy. So each firm maximizes its profit. So the firm's profit given one production plan can be expressed as a dot product between price vector. So price vector is a L-coupled vector. So price of each commodity and the one production plan. So it should be feasible. So Yj should be element of production set. Okay, so that's the firm side. So the basic elements can be summarized by these three. So on consumption side, we have a consumption set, the set of bundles that can be chosen by consumers, and preference relations, and the firm's ownerships, theta I. And production can be described by just a production set itself. So we have a J production sets and total endowment. All right. And the only example we studied in chapter 15 are special case of this general framework. So in 2x2 pure exchange economy, there are just two goods. So the number of commodity is a 2. And there are two consumers, so the I is equal to 2. And we did not consider production, meaning that there is no ownership and there are no firms, so the Y sub j should be empty set. So the more exact expression is theta I is equal to 0, and Yj is just an empty set. meaning that there's no production in this Edgeworth or pure exchange economy. Okay, so the basic component of exchange economy is just xi and preference relation for I consumers and no production and just endowment. Okay, so these three components characterize a one pure exchange economy. So that is a one example of this general framework. Robinson Crusoe's economy, there's just one agent, so I is equal to 1, and there are two commodities because that consumer can use working hours for production and for consumption of leisure. And there was another commodity produced by one firm. And that firm was fully owned by this consumer. So theta 1, that was equal to 1. So we assume the full ownership, right? One agent engages in consumption and production at the same time. So the firm is fully owned by the consumer. Of course, that is an unrealistic assumption, but that was just the example. And the number of firm is equal to 1, right? So there is only one production set. And endowment was given by that L bar, so 24 hours or 16 hours, whatever. So that's a Robinson Crusoe economy, also special case of this general framework. And finally, 2x2 production economy, and we didn't consider production side, consumer side. We only consider production side, right? So I was equal to 0, and there were two inputs, so there are two commodities, and Z was 2. And endowment was so the endowment of factor 1 and factor 2. Okay, and so remember, these commodities are not just for consumption. Some commodities stand for inputs. Okay, so all examples we studied in chapter 15 are special cases of this general framework. All right, so we first define feasible allocation. So on allocation in this economy, should specify consumption bundles for each consumer. So from x1 to xi, so the consumption, also the allocation of L commodities for each consumer, and the production plan for each firm. So from y sub 1 to y sub j. Once again, let me use a superscript for consumer indices and a subscript for firm indices. Okay, so one allocation is a specification of a consumption vector for each consumer and a production vector for each firm. So production plan or vector for each firm. Okay, and we say one allocation is feasible if for each commodity K, aggregate consumption, so x sub ki, summation of x sub ki, where I goes from 1 to I, so this is a total demand for commodity K. Okay, and what is a total supply of commodity K? So there are first a initial endowment of commodity K that is given by omega K bar, and some additional commodity K might be produced. Okay, so we have to add up this entry y sub kj. From now, j goes from 1 to j. Okay, so this is a quantity per commodity, so total quantity K, commodity K, produced by J firms. Okay, so in the pure exchange economy, because there was no production, so this term was this term that did not exist in that pure exchange economy. But now we consider production as well. So in the presence of production, we have to add this term to the initial endowment. So this is going to be total supply of commodity K, right? So this equality implies we assume that no free disposal assumption. Okay, if there is a free disposal, then feasible allocation is going to be this inequality. So if in order to dispose some commodity, if there is some cost, and feasible allocation will be this equality. Okay, so aggregate consumption, aggregate demand should be equal to aggregate supply, total supply. All right, and the Pareto efficiency. So we say one feasible allocation. So efficient allocation must be feasible. Okay, allocation is Pareto optimal. If there is no other feasible allocation x prime and y prime such that all consumers prefer x prime to x and some consumer strictly prefer x prime I to xi. Strictly prefer. So we have to eliminate this notion. So xi for some I. Okay. So if there is no other feasible allocation x prime and y prime satisfying this relation, then we say allocation x and y is Pareto optimal. Okay, so the natural interpretation applies. So there's no other way to improve some consumers' utility, some consumers' welfare, without hurting the some other consumers. Okay, so if someone gets better off, the other consumers naturally gets worse off at that Pareto optimal allocation or Pareto efficient allocation. Okay, so this Pareto optimal allocation does not concern distributional issues. Okay, so for example, distributing all endowments to one consumer in that pure exchange economy, say in that edge of the box, Pareto set is a Pareto set. So the set of all efficient allocations is going to be one curve inside the edge of the box. So even these two extreme allocations are Pareto optimal. Okay? So this is a origin for consumer A, and this is origin for consumer B. So this allocation means consumer B. So all units, all endowments are allocated to consumer B, and this is all endowments are allocated to consumer A. So even that extreme allocation is Pareto efficient, because if we distribute that allocation to other consumer, then that consumer will be worse off. So this Pareto efficiency, this notion, has nothing to do with distribution issues. Okay. So second welfare theorem complements this drawback, because that theorem tells us now if we concern some distributional issues, even that allocation can be achieved by the use of a market mechanism. So this is why we need a second welfare theorem, because just the Pareto efficiency alone, we can't guarantee some desirable policies. Okay, so we can guarantee the desirable allocation from the market mechanism itself. All right, and then next, let me define Wallachian equilibrium. So equilibrium is so now we have two elements in large. So one allocation. So the consumption plans and production plans for each consumer and for each firm, and price factor. Okay, so the price of each commodity from 1 to L constitute a Wallachian equilibrium if these three components satisfy these three conditions. So first, on production side, each production plan has to maximize from J's profit. So Y sub J star from J's production plan, it should be feasible. Okay, so you say it belongs to production set Y sub J. It has to maximize from J's profit. So in math, we can write this as P star dot. So at this price factor, from J's profit, by choosing this production plan, that is a maximized profit, meaning that this value is higher than P star dot YJ for all feasible plans, for all YJ in the set YJ. Okay. So the chosen production plan, the equilibrium allocation for firm J, that production plan has to maximize from J's profit at this equilibrium price. Okay. So at given P star, YJ star should maximize from J's profit. So this is after midnight. I'm now repeating, what I said over and over. Okay. And the second condition is now on consumption side. So the allocation for each consumer should maximize consumer I's utility given budget constraint. So in math, we can write this as UI, consumer I's utility at equilibrium allocation, okay, should be higher than utility at other bundles for all xi in the budget set, BI, okay, consumer I's budget set. And we can define budget set as, in this economy, as a, so BI, that is a function of P star and the omega and theta, okay? That is a set of bundles in consumption set xi such that P star dot xi, so total expenditure for consuming this, for choosing, so total expenditure necessary for choosing xi, bundle xi, at price vector P star should not exceed consumer I's worth, so WI, but WI is, so this consumer has initial endowment omega, so the market value of that endowment, so we can write this way, dot product between price factor, equilibrium price factor, and the initial endowment, right? And furthermore, each consumer has a ownership shares in several firms, okay? So we have to add a profit here, just as in Robinson Crusoe's economy. The consumer has a full ownership of the single firm, right? And we add the maximum profit to the wealth, right? So likewise, we have to add a profit that is a theta ji, okay? So for each from J, from I, our consumer I owns a share as much as theta ji. So the consumer I retains the right to have this amount of profit, P star dot YJ star, okay? So that is a maximum profit of from J, and consumer I has a share as much as theta ji. So this is going to be an additional wealth from that ownership, okay? and then we have to sum this profit from from j equal to 1 to capital J. So that is a basic constraint. Hopefully this is readable. Let me write down here one more time. So in that general framework, budget set BI is a set of bundles such that P star dot xi should be lower than P star dot omega I. So this is a total. This is a market value. Total endowment plus sum of theta ji times P star dot yj star. So that from J's profit times consumer I's share on the share in from J. Okay, and from J equals 1 to J. Okay, so these two terms so consumer I's wealth will consist of these two terms. So we may call this consumer I's wealth WI. All right, so that is a equilibrium condition on consumption side. So consumer I's utility must be higher than at the equilibrium allocation. So consumer I's utility must be the maximum at that equilibrium allocation compared to utility at other bundles, other feasible bundles. And finally, we need a market clearing condition. So all markets must clear at the equilibrium price factors, P star. Okay, so market clearing condition is just a feasibility condition. So total demand for commodity K by consumers should be equal to total supply. All right, and here's one more notion that is a market equilibrium or price equilibrium with transfers, but that is related to second welfare theorem. So let me explain this next week. Okay. Now let me prove the first welfare theorem. So we now present the formal proof of the first welfare theorem. That is a confirmation of Adam Smith's invisible hand property, that invisible hand property of the market mechanism. Okay. So simply Wallachian's equilibrium is Pareto optimal. Okay, so that supports a laissez-faire policies. So the government does not have to intervene in the market. All right, and for this theorem, we need just one weak assumption. So only one assumption is necessary for this result. Okay, so this result is quite general. Okay, and the assumption on the consumer's preferences. That is a local non-satiation assumption. So I think you've ever seen this. I think you have seen this assumption when you study chapter 3 in Musgrave and Winston Green. So locally non-satiated assumption implies that for every bundle xi in the consumption set, and for every epsilon, there exists another bundle xi prime in the consumption set, such that in the neighborhood of that bundle xi, we can find an additional bundle xi prime, such that consumer I prefers xi prime to xi. Okay, so put another way, this assumption eliminates thick indifference curve. Okay, suppose an indifference curve is like thick, meaning that every bundle in this region is indifferent. if the indifference curve is thick like this, then in that bundle, so if we choose bundle X, then in the neighborhood we can find some bundle Xi prime such that consumer I strictly prefers that Xi prime to chosen bundle X, right? So this is an example of this assumption is violated. Okay, so whenever this assumption is satisfied, we have a single curve, a single indifference curve passing through some bundle X. Okay, so this curve separates the consumption set into two regions. So in this region below the curve, this is this is the set of bundles consumer prefers X to Y. So set of bundles Y, so the bundle X is more preferable than Y. Okay, and this region is the set of bundles Y, which is more preferable to bundle X. And the on the curve, we have the bundles indifferent to bundle X. Okay, so this local non-satiation assumption rules out the possibility that indifference curve have this some region, then the assumption is violated. Okay, now with just a weak assumption, we can prove the first welfare theorem. So if preference relations are locally non-satiated, then the Wallachian equilibrium allocation is Pareto optimal. Okay, so that's a statement of first welfare theorem. All right. Before proving this statement, let me explain why we need local non-satiation assumption. So suppose that consumer one's preference relations do not satisfy that local non-satiation assumption. So consumer one's indifference curve is thick like this. Okay, now it's some thick stripe. So any boundaries inside this stripe are indifferent to consumer one. Okay, and think about this allocation X star. So if that X star, we have a equilibrium price, so P vector P. Okay, so that supports this allocation as an equilibrium because at this price vector, consumer 2 maximizes his own utility, right? Bundle X, actually this allocation provides a highest utility given this budget constraint. Right? This within this budget set, this X star maximizes consumer 2's utility. And this X star also maximizes consumer 1's utility, right? Because consumer 1 can do better than can achieve a high utility by choosing other boundaries than X star, right? So this is an equilibrium. That X star satisfies all conditions, all equilibrium conditions. By the way, this is a pure exchange economy, edge-of-the-box economy, right? But is it a Pareto optimal allocation? The answer is no, because without hurting consumer one, because to consumer one, this X star and allocation X are indifferent because these two allocations are in this stripe, right? But so consumer one feels indifferent between these two allocations, but consumer two strictly prefers allocation X to allocation X star. So there is a way to improve, one consumer's welfare without hurting the other consumer's welfare. So allocation X star is an equilibrium, but not Pareto efficient. Okay, this is why we need a local non-satiation assumption to eliminate this kind of possibility. Okay. Anyway, so not Pareto optimal. Now let me prove the welfare theorem. Okay. So the proof is based on the revealed preference theory. So if you have some trouble with this revealed preference theory, you may refer to chapter 2.f. But we are going to use very intuitive preference theory. So I think the proof is very clear. Okay. So first, let's think about the implication of that local non-satiation assumption. Okay. If indifference curve is every indifference curve is just a single curve, then at the utility maximization bundle, so at the optimal bundle, basic constraint has to be binding. So for every consumer, if xi star was a maximizing consumer i's utility, then at this choice, basic constraint should be binding. Okay? This may not hold without this local non-satiation assumption because going back to a previous slide, all right, so this x still maximizes consumer 1's utility, but this x, at this bundle, basic constraint is not binding because a consumption so consumer 1's budget set is this triangle, and this allocation x is inside the triangle, meaning that at this allocation x, consumer A does not expand all resources. Okay, so there's some money in the pocket. Okay? But with this assumption, we can make sure all resources are expanded for utility maximization. Because there is another bundle in the neighborhood, of any bundle. Consumer I strictly prefers that bundle to bundle X. So by the local non-satiation assumption. All right, so we have this. Once again, this W sub I has some complicated expression. It was a P star dot omega I plus theta ji P star yj star. Okay, and summation is so where the script j goes from 1 to j. All right, so the equilibrium allocation is denoted by x star and y star, and then the proof is by contradiction. So suppose to the contrary that equilibrium allocation is not Pareto optimal. That means there exists another feasible allocation x prime and y prime. Let me write down here because now I'm really tired. So just to make sure I do not make any mistakes, let me write down here. So if x star and y star is not Pareto optimal, it means there exists a feasible allocation x prime and y prime such that some consumers, so every consumer prefers x prime. So x, and let me use a consumer index first. So x super n prime is preferable to x n star for every n, for every consumer n. Okay, so every consumer n weakly prefers that allocation x prime to x star. Okay, so this relation just means that so it does not hurt any consumer's welfare. Plus, there is a one consumer I who strictly prefers x prime to x star. Okay, then this allocation x star y star is not Pareto optimal. Okay. All right. Then now we use limited preference theory. So what limited preference theory tells us, if a so think about a very simple example. So that there are just the two consumption goods, X1 and X2. Okay. And suppose that consumption I chooses this bundle optimally, for his own interest. Once again, by a local non-satiation assumption, optimal bundle should be on this budget line, right? So consumer chooses this bundle X star instead of X prime, okay? But nevertheless, consumer I strictly prefers X prime to X star, okay? That means this bundle X prime was a not feasible, was a not affordable. If that was a affordable, so if the bundle X prime was in the triangle, then this X star is not a maximizing consumer I's utility. So consumer I would have chosen X prime because that was affordable, right? Instead of X star. Okay, so contradicts that contradicts that assumption. Xi star maximizes consumer I's utility. So if consumer I strictly prefer Xi prime, bundle Xi prime to Xi star, that means Xi prime is outside the budget set. Okay, at the equilibrium price factor P star. Okay. So in math, we can write this situation as xi prime. So in order to consume this bundle at price factor P star, then total expenditure necessary is higher than what he has, his wealth, right? And the same interpretation applies to these preference relations. So if every consumer N prefers X prime to X star, okay, then nevertheless, they chose a X star because that X star was a equilibrium allocation, so maximizing each consumer's utility. Okay, so that means in order to choose this X and prime, now this is a weak preference. So we allow the possibility that that bundle is on the budget line. Okay, so consumer chooses X star instead of X prime. Because those two are indifferent, right? Maybe indifference curve is a flat, so line segment in this region. So the two bundles might be indifferent. So the consumer randomly chooses a X star instead of a X prime. Okay, we allow for such a possibility, but that is just a weak preference, right? For consumer I strictly prefers X prime to X star. So this bundle should be strictly outside of the budget set. Okay, but for other consumers, we apply that weak preference. So we should have a weak inequalities here. All right. So now let me put these all inequalities together. Then what do we get? So we have a total I inequalities because for consumer I, this inequality we have, and for other consumers, we have a I minus 1 inequalities. So if we add all together these inequalities, and on the right side, we have a total wealth. So I1 plus, the other consumer's wealth. So that is a total wealth. Okay. On the left-hand side, we have total expenditures necessary for choosing this bundle X prime. Right? So we do summation over consumer I. Okay? And then the total wealth is, because each consumer has this wealth. Right? So if we do summation over I, okay, so summation over I, then P star dot summation of omega I, and we have double summation over I and j, theta j I, P star, yj star, okay? But we can interchange these two summations. So we first add over I, and theta j I, P star, yj star. And if we add over I, that means a full ownership. So that is equal to 1. So this is equal to 1. Okay, so that goes away. So we can write the total wealth as a P star dot, this is not W, but omega I, consumer I's total endowment, okay, which is a omega bar, total endowment, and yeah, the total profit by, it's accrued to firm J's, every firm J. So total profit accruing to every firm J. All right. And furthermore, okay, now we are almost done. Equilibrium production plan YJ star, due to the first equilibrium condition, it has to maximize the firm J's profit. So must yield the highest profit for each firm J at price vector P star. Okay, that means P star YJ star should be higher than P star dot any yj. So for all yj in the production set yj. Okay, so that includes a yj prime. Yj prime. I mean the alternative allocation. That Pareto dominates this equilibrium allocation. So with this inequality, we can write this. So we can set up the lower bound for this one. So this one is weakly higher than P star dot omega bar plus summation of profits at allocation y prime. Right, because this inequality is held for every firm J. Equilibrium allocation, so the production plan YJ star has to maximize from J's profit. Right? So if we take this one and this one, so we have a chain of inequalities. So let me take the expression on the very left side and the expression on the very right side. Then we have a strict inequality right here. So we end up with this inequality. Okay, this one should be strictly larger than this one. Okay, and P star are common, so we can delete this P star. Okay, that means summation of xi prime is a strictly larger than total endowment plus total production. So that means x prime y prime is in fact not feasible plan. Okay. For Pareto dominance, you know what? Going back to Pareto efficiency definition, there should be so if this was a not Pareto optimal, then there is some another feasible allocation x prime and y prime. That Pareto dominates this previous allocation. But we select a one candidate, x prime, y prime. So we deny that conclusion. So the allocation, we first start with supposition to the contrary. So the allocation is not Pareto optimal. That means we assume there exists a feasible allocation x prime and y prime, which Pareto dominates that equilibrium allocation. But it turns out that this allocation is not feasible. So that is a contradiction, right? So this contradiction proves that equilibrium allocation is in fact Pareto optimal. Okay. So let me discuss this theorem very shortly. So we make a very weak assumption for the validity of this statement. First vector theorem holds under just a very weak assumption, local non-satiation. Okay, but in fact, we already made two strong assumptions: market completeness and price-taking behaviors. That is a assumption of a market mechanism. But once again, these two conditions are not satisfied in the presence of externalities due to undefined property rights. And if some firms have a market power, or if some or for some commodity, there are some so if there is a one single consumer, that is a monopsony. I'm a little confused with the terminologies now. Okay, but if some consumers or firms have a market power, that means they are not price takers anymore. Then this price taking behavior assumption is violated. And if there is an asymmetric information, so the price information is not fully shared or not fully disseminated in the society, then the assumption also is violated. In either case, no longer does the market mechanism lead to an efficient allocation. So it looks we impose very weak assumption for the first derivative theorem. The underlying assumptions are quite strong. Okay, so we have to be careful about the interpretation of this first derivative theorem. And the second drawback of this theorem is silent about the desirability of the equilibrium allocation from a distributional standpoint. So Pareto efficient allocation means all resources are used for all resources are used in an efficient way, but it's silent about fairness or equality and so on. Okay. So Pareto efficiency does not guarantee that is indeed a socially desirable allocation. Okay, and in fact, second welfare theorem complements this issue, especially a distributional distributional issue. So showing that any socially fair, so achieving some income inequality or wealth inequality, and efficient allocation can be achieved by the use of a market mechanism. We are going to study this in the next week. All right. So I think the last video is a little bit long. It takes a little bit more time than I had expected because now I'm really sleepy. But anyway, so in this video I introduced a general framework of a general equilibrium model. And I presented a statement of first welfare theorem, and we proved that statement in a general framework with a very weak assumption, and we discussed the implication as well. All right. Hope you guys enjoyed this video, and I will be a little bit more punctual about the upload timing. So this week, I was a little bit exhausted on yesterday. So, and then the slide was not fully ready yet until the Tuesday night. So the upload timing is a little bit late, and sorry about that. But the next time I will be more punctual. Okay, and hope you guys enjoy your full week, and see you guys next week.